Swayam Prabha. Digital India. Educated India.
So, welcome back. Today we are ready to start a slightly new topic. So far in our course we have investigated methods to construct solutions, where essentially we begin with a start state and look for a goal state. But very often we think of problems differently. We think of a problem as made up of sub problems, and we break down the problem into sub problems and try to solve them. And there is an approach which takes this strategy, and this is what we want to look at today. So, this area is called problem decomposition, because we are breaking down a problem into smaller problems. So, a quick recap of what we did so far. Our view of problem solving was based on state space search. It was centered around the state. The state space was the arena over which we searched, and the solution is expressed as a sequence of state. And we had seen this, that even when we move to solution space, the solution was still expressed as in terms of states. Now, we are moving on to something which is a little bit different, which takes a goal directed view of problem solving. The emphasis is on breaking down a problem into smaller parts, a little bit like what we did when we looked at backward state space planning, where we regressed from a goal to sub goals and did that. This approach has a similar flavor, that we are thinking in terms of the goal we want to achieve, and trying to also exploit the fact that problems have sub problems which can be solved independently. So, in this space in which we look at a goal directed approach to problem solving, we have two kinds of problems. One which are called solved. These are primitive problems for which you do not need to do anything further, and the other kind of nodes in our space, search space, would be live nodes, and they would need refinement. And this is a little bit similar to what we did when we looked at the SSS star algorithm for game playing, in which we had partial solutions which needed to be refined further and so on. In fact, as we study this approach, you should try to compare it with the algorithm SSS star that we developed earlier. So, let us start off with some motivation first, and as a motivation, let us look at a problem which has typically three parts. And let us say this is a problem of planning an evening out with friends, and let us say you are the one who is proposing the plan, and the basic idea is that you must do some activity followed by a movie and followed by dinner essentially. And the plan, you are working with something which is like a move gen function which was in the state space. It would be as follows, that in the start state you first pick an activity, then having chosen an activity you pick a movie to go to, and having picked a movie you pick a restaurant to dinner, and you propose this as a plan to your friends. If they accept it, it is good, you can go ahead and execute it. If they do not accept it, you backtrack essentially. And the algorithm that we are just looking at now, as a precursor to what we want to look at, is essentially depth first search, and this is how the search space would be explored essentially. Remember that this is basically depth first search, and remember that your problem solution is in three stages: pick an activity, pick a movie, and then pick a restaurant for dinner. And only when you have picked all three will you ask your friends, is that okay? So, this is how depth first search would start. You pick some activity, let us say the most common activity nowadays, visit a mall, and then you say you will go and see the film Matrix, and then you would have dinner at Pizza Hut, and you present this to your friends and they say no, somebody objects to it, and then you do this depth first search over these possibilities, and this is how you explore the rest of the search space. So, instead of Pizza Hut, you propose Saravana Bhavan, then you backtrack and you say, okay, maybe instead of Matrix, you would see AI the film, and again you propose Pizza Hut and Saravana Bhavan, it does not work. Then you propose Bhuvan Shom the film, and again Pizza Hut and Saravana Bhavan, and so on. The search continues, and then eventually you backtrack all the way to the start and say, okay, maybe we should go to the beach, and then you propose the film Matrix and Pizza Hut, and then Saravana Bhavan, and at this point let us say your friends accept and say, and so what is the plan? The plan is visit the beach, watch the film Matrix, and then eat at Saravana Bhavan. Now, if you look at this space that you have explored carefully, you would see that probably the culprit choice was the mall essentially, because if you look at the solution that we have looked at, which is to visit the beach, to visit the Matrix, and to see the film Matrix and go to Saravana Bhavan, of these two, which is the Matrix and Saravana Bhavan, were there earlier also, and the only thing that changed from the accepted plan to the rejected plan is that there was a mall visit. So, maybe that is a culprit, but searching the space using depth first search does not allow you to identify that. In fact, this entire search tree that you have see on the left hand side covered in colored in reddish color is a waste of effort, because having chosen the mall, if the mall is a culprit choice, then you whatever you do subsequently is not going to lead to your solution essentially. But depth first search does chronological backtracking. So, after being rejected for a solution, it first backtracks and tries a different film or a different restaurant. Then if that does not work, it go backs and tries a different film and so on, and even only when it has completely explored this side where the first activity was mall, that it backtracks and goes to the second activity. Now, in the community of constraint satisfaction or constraint processing, people have worked out with solutions where instead of chronological backtracking, you can, as they say, jump back to a relevant node or a culprit node. If you can somehow identify that the solution, for example, the first solution, that visit mall, the Matrix, the Pizza Hut, or even after the second one, which is Saravana Bhavan, you realize that it is a mall which is the culprit, you go back to that variable and then change the value of that variable. That kind of an approach is called dependency directed backtracking, and if you ever study constraint satisfaction problems, you would encounter various algorithms which take different approaches to jumping back to culprit nodes. If you were to look at the complete search tree that of the options that were available to you, the options that in this small example we have are either go to the mall or go to the beach, and either eat in Pizza Hut or eat in Saravana Bhavan, or one of 4 films, the Matrix, Bhuvan Shom, 7 Samurai, and or 3 films, Matrix, Bhuvan Shom and 7 Samurai. So, let us say what we have depicted here are the 2 solutions that would have been accepted by your friends. The one on the left, which is the beach, the Matrix and Saravana Bhavan, is the one that you encounter first when you are solving the problem using depth first search, and maybe there is a second solution that you could have possibly proposed, but in this case you did not have to, which involves watching the film Bhuvan Shom. Yeah, the fourth film is AI the film essentially. So, there are 4 films, 2 activities and 2 restaurants. Now, it makes much more sense to look at this problem. Now, this problem has clearly 3 different components, which is to organize the activity, think of a film and think of dinner. So, the search space that we are interested in looks something like this essentially. So, at the top level this thing, and this is called an AND OR tree, and we also have AND OR graphs, as we will see in some examples. So, there are 2 kinds of nodes here, one are AND nodes. So, the topmost node here is says that you have to plan an activity or plan an outing, and those 3 edges coming from there. connected by this arc, you can think of that as a hyper edge or a hyper arc, and it is an AND arc essentially. It says that to plan an activity, you must plan an outing, you must plan an evening activity or outing, you must decide on a film, and you must decide on where to have dinner. So, these are 3 separate problems, but the fact that they are depicted in an AND arcs means that you have to solve all 3 of them essentially. And then at the next level, when you are talking about the evening activity, which is the outing, you have 2 choices, either you visit the mall or you visit the beach, and this problem of evening activity is completely separated from the rest of the problem, other 2 problems, which is movie and dinner. So, likewise movie and dinner have their own choices, and these are all choices. So, this kind of a space that you are searching is called an AND OR tree, and if there are common activities, it can be called AND OR graph. You could have, we will see an example where it is a graph and not a tree essentially. Now, the important point to observe here is that the solution is a subtree, unlike in the state space approaches that we have seen, where the solution was a path from a start state to a goal state. Here the solution is a subtree. Of course, you might remember that when we looked at algorithm SSS star for playing games, there the solution was a strategy, which was also a subtree of the game tree. And you will find more similarities as we go along, looking at this approach of solving problems using AND OR trees or AND OR graphs essentially. Okay. The leaf nodes in this space are the solved nodes, which means you do not have to refine them any further essentially. Of course, if you are working with a different level of detail, then for example, the visit beach node would have been further broken down into sub steps and so on, and the kind of stuff that we talked about when we did hierarchical planning, or even when we looked at mean sense analysis. We will do a quick recap of mean sense analysis after we have done with this topic, but it is a level of detail that may be different essentially. But in an AND OR tree, the leaf node is a solved node, which means you do not need to refine any further, because in this case you are simply trying to make the choices where to go out, what movie to watch, and where to have dinner. We end the problem solving phase here essentially. If you were to do the whole thing autonomously, they may have been further refinement of each of those 3 components of the solution, which is visiting the beach and going to the matrix. For example, you have to buy tickets and all this kind of stuff and so on. In this case, as we saw, there were 2 options, that your friends wanted to go to the beach clearly, because all the options with mall were rejected. So, that is definitely not a candidate, and also at least in the case of the matrix of film, we saw that Pizza Hut was rejected, but Saravana Bhavan was selected. But we had seen in the space that we were looking at earlier, that Saravana Bhavan, that Bhuvan Shom would have been a candidate film as well, and that is kind of reflected here in saying that it is another possible choice here. So, you could have 2 solutions, and the movie choice could have been either matrix or Bhuvan Shom, and you would have a subtree which is a solution. Now, from the very beginning, and this is more than 50 years ago, people have realized that AND OR trees are a good way to represent many problems, and one of the problems that has been addressed using AND OR trees is the problem of symbolic integration, which you must have surely studied in your early engineering days or late school days, and it is a thing which requires a tremendous amount of knowledge about how to transform problems into other problems which can be solved easily. And this is the flavor of problem decomposition, that you have a problem to solve and can you transform it to another problem which can be solved more easily, and you repeat this process till the transform problem is so primitive that you do not need to refine it any further. That is the flavor of and solving AND OR trees. So, in this example we will not go into the details of this particular integration problem, but it seems difficult enough looking at this thing. And there are various things that you could try. For example, you could substitute x with sin y and you get the second part, which is sin raised to 4 divided by cos raised to 4, which you could either replace, solve it by cot inverse or tan raised to 4, or break it up into something which looks even more daunting. And then this tan raised to 4, let us say we go by this choice, we have reduced it to z raised to 4 by 1 plus z raised to 4, and that itself you can do using integration by parts, which means that now this larger problem that you have broken up it into 3 parts, which is -1 z square and 1 over 1 plus z square, and these 3 parts are connected by an AND arc, and then eventually you come down to very primitive this thing. So, for example, integral of dw, you do not have to worry about any further, and integral of z square, for example, we assume that there is a lookup table or something where we know the values of these things, and likewise for the third part, which is 1 by z 1 plus z square, you can substitute z equal to tan w and eventually reduce it again to dw essentially. Now, the substitutions that you have made on the way will have to be back substituted to construct the solution, and eventually if you are really inclined, you can go back and see that the solution has those 3 parts which you got from integration by part, and what we see here is the result of back substitution. So, symbolic mathematics is very popular nowadays, and there are many approaches. We started with a program called Saint long time ago, then somebody interested a program called Sin, then there was a commercially available piece of software called Maxima, and now MATLAB of course allows you to do this sort of a thing. Another problem where AND/OR tree is really shown was in this program called Dendrol, which was called an expert system, and around that time, the 70s and the 80s in the last century was in some sense the wave of expert systems, just like nowadays there is a wave of deep neural networks. At that time, there was a wave of expert systems, and Dendrol was one of the pioneering programs which led that whole activity. In fact, it is seen as one of the earliest successes of AI developed at Stanford University. This Dendrol program is basically in 2 parts, dendritic and algorithms. So, it got its name from there. It was one of the first programs to emphasize the power of specialized knowledge over generalized problem solving methods. So, we have seen throughout this course that search based approaches to problem solving, which are general approaches to problem solving, run into this what we call as a monster called convex or combinatorial explosion or exponential growth, and we had been struggling to find various ways of trying to overcome that. One of them was the use of heuristic functions, but Dendrol took this to one step further, and it says that you can use specialized knowledge to solve problems, and this specialized knowledge that we are talking about is something that in the community that was working on expert systems said that we will extract from human experts. So, the idea was that you talk to the experts, and there used to be protocols for extracting knowledge, and extract that knowledge and put it in the form of some standardized representation, typically rules. We will look at rule based systems a little bit later, and then use some general purpose algorithms to work with that knowledge essentially. So, that was the notion of specialized knowledge. We will come back to that later in this course. The task that Dendrol was working was to assist chemists in the task of determining the structure of a chemical compound. Now, if you have studied chemistry, you would know that you have molecular formulas and you have structural formulas. Structural formulas tell you how the atoms in that particular compound are arranged. Now, given one molecular formula, there may be many different structural formulas associated with it, and that would result in different materials. And for example, carbon is a classic example. It can be coal or it can be a diamond, but it is all carbon arranged in different ways. So, the problem with the chemists are facing was that the number of candidate structures can be very large, running into hundreds of thousands or even more, and it was a painstaking task for them to propose relevant structures and verify, and verification was done by taking the spectrogram of that structure and testing whether it is really matching with the spectrogram of the real material that you are working with. So, anyway, the problem was that the number of structures that they wanted to explore could be very large, and this was where Dendrol came in. It led to a program called ConGen, which stands for Constraint Generator, that allows the chemist to constrain the generation of candidate structures in such a way that they have to inspect only a few towards the end essentially. So, here is an example of what you mean by structural formula. So, the compound here is as you can see C6H13NO2, that is a molecular formula for the compound, but those atoms, the 6 carbon atoms, the 13 hydrogen atoms, 1 nitrogen atom and 2 oxygen atoms can be explored, can be arranged in different ways essentially. So, in this diagram that I have drawn here, which has been taken from this paper by Buchanan, we have not drawn the hydrogen atoms, but you can imagine that given that the valency of carbon is 4, there would be one hydrogen atom here, another here, another here, one here, one here, and so on essentially. So, 3 here and 2 here and 3 here essentially. So, I am also not drawing the entire set, but you can imagine that that would be the final this thing, but since hydrogen atoms can obviously be filled in the diagram, we have not shown them. So, which of these is really the material that we are looking at? That is what the task that Dendrol was helping the chemists to solve essentially. Now, this kind of depicts the kind of search space that Dendrol was exploring. So, here we have drawn it for a smaller formula, which is C5H12, and you can see that there are, in this diagram, there are 5 different choices of how to try and explore different formulas. So, some of those are OR choices like the one in the center, but some of them are AND choices like for example, here or for example, here. And so, this AND choice says that if you want to look at this particular compound, then you have to solve for C2H5, you have to solve for C2H5, which is shown here, C2H5 here and C2H5 here, and both have the same solution, and that is why, as I said some time ago, the search space can be a graph as opposed to a tree. It does not have to be a tree, but the ones shaded here are completely solved, which means there is nothing unknown about the structure, and those could be candidate solutions that Dendrol would explore. So, the program Dendrol essentially explored an AND/OR graph. These are also called AO graphs, and it generated candidate structures and then generated a synthetic spectrogram for each structure and compared the synthetic spectrogram with the real spectrogram of the material, and based on that it would decide whether it was a good hypothesis or not. It turned out that it performed better than most trained chemists, and it is an example of what was then called an expert system essentially. So, these are 2 examples which are there to motivate us to study how to explore AND/OR graphs, and we will do that in the next session, where we will look at this idea of gold trees. So, meet you then.